Okay, now we're going to start looking at capacitive networks. Okay, and networks are just a lot of these things connected. Well, this one we just did. It's not too bad. I want to show you how I do this in a structure. I have a column for capacitance, charge, and voltage. And since these are in microfarads, I put these in microfarads and these in microcoulombs. So what I do is I list all the capacitors that I have. So I'll just call it, I'll actually write C1, C2, C3. Because sometimes what happens in more complicated networks is when you combine things, you sometimes end up having two capacitors, like an equivalent will have the same number as another one. So it's nice to know what we're talking about there. So C1, C2, C3. So 4 microfarads, 3 microfarads, 5 microfarads. And we know that the voltage difference across the 4 microfarad is 9 volts. 9 plus minus. Those longer lines indicate the positive side. Okay, so that is 9 volts across that. And look, they're all connected there. 9 volts across that, and indeed, for that last one, 9 volts. So what we can do now is we can take our approach for finding Q. Q is just going to be C times V, and that will end up being 36 microcoulombs, C delta V. Okay, and then hang on just a second, and this one will be 27 microcoulombs, and this will be 5 times 9, 45 microcoulombs. And we're going to replace it with 1. And it's funny, they draw these batteries. Those are supposed to be individual cells. I'm not going to be as fussy about that right now. This is just a battery, 9 volts. And so for this is going to be my C equivalent. Didn't write it well. C equivalent. The voltage across it is also 9. The equivalent, well, there's two things I can do here. One thing is I can add up all the charges, which would be 9108, and then I could use Q divided by V ends up being 12 microcoulombs. So in other words, I use those two to find that. Or, since they're parallel, I can just say, I can replace that with 4 plus 3 plus 5. 7 plus 5 is 12 microfarads. So this is 12 microfarads. Okay? Now in some of these what happens is you go in this direction, redrawing and simplifying, putting new entries in there, and you may have to do several steps. Then you reverse, you go in the other direction. Okay? In this case we didn't have any blanks in there, but in some cases we will. So I'll show you how that works. Now let's get to this one. This is a series, and what we have is, I'll go C1, C2, C3. The capacitance is 4 microfarads, 3 microfarads, 5 microfarads. The voltage difference is between here and here, right? That side's connected to the bottom of C3. This one's connected to the top of C1. So we do not know the voltages. Okay? So now we've got a little bit of an issue. We've actually got to figure out how we're going to do this. Okay? So the first thing we look at here is we know the charges will all be the same. Okay? We know the charges are going to be the same. So what we need to do is combine those. So we're going to combine those into one capacitor using the rule that we had on the previous couple pages back. Okay, so this is still 9 volts plus minus. So there's still 9 volts across the whole thing. So I'm going to replace all these with a C equivalent. So you can see we're going to have to work backwards because we've got all those gaps there. And across that C equivalent is 9 volts. Okay, the equivalent, 1 over 4 plus 1 over 3 plus 1 over 5 equals 1 over C equivalent. Okay, and when you plug that in, 4x negative 1 plus 3x negative 1 plus 5x negative 1 equals, and then you do inverse, you end up with an answer of 1.28 microfarads. Okay, so the equivalent is 1.28 microfarads. So we got those. We went through this whole process to get the equivalent. Now we can use these two to find Q. C times delta V gives you Q, and that's 11.5 microcoulombs. Okay. Well, remember what we said. The charges in series, the voltages aren't the same, but the charges are. So 11.5, 11.5, they each have 11.5 coulombs on there. Then we can come over here and we can say C equals Q over V. So V is Q over C. And what we end up with is 2.875. So in other words, now we're going and we're moving that way. 2.875, 3.833, and 2.3 when you plug those in. I hope you're pausing and doing the calculations yourself. Now, when you look at this, there's another thing that's very interesting that ends up being really important. Remember we talked earlier about if the potential energy, the potential difference between this conductor and this conductor is 9 volts. That means the potential difference between here and here, here and here, and here and here also has to add up to 9 volts. In other words, if this wire has 9 joules per coulomb more energy than that, then this over that, how much more this has over that, how much more this has over that, how much more this has over that, has to add up together. Well, look what happens when you add that. That's 7, 8.7, that's 9 volts. So just tying this together, the sum equals 9 volts. Okay, sum of the VIs. Okay? Now let's go to something a little bit harder. And just to get a sense of how this works, this is what we're going to be doing. We're going to combining parallels and series that as possible and simplifying. Okay, now when we look at this, these two capacitors look like they're in series, but remember, we can't have something branching off. They have to just be like if they were like this and this, right? That's series because these two ends are connected together. Nothing's coming off that. But this one, those two are not in series. So you got to be really, really careful about these. These look in parallel. They are, but you can't just add all three of them because this one's not in parallel with this. So what we can do is this is definitely a series combination. So what we can do is use our series equation when we have the numbers and pull that out, and we've got to maintain the connections. So this one's still over here. This one's up here. So we're going to replace that with 1, our equivalent. I'll call it our equivalent. I'll call it C series. When we simplified those, we're going to have a value for that. 1 over this plus 1 over this equals 1 over that. We solve, and that's our new capacitance. Now look, those two are definitely in parallel, and I can tell because that end and the opposite ends are connected together. So we can then redraw. I'll redraw it over here. Leave that battery alone. I leave all the other connections the same, right? So there's the rest of the circuit, but I replace that with, I'll call that C parallel when I combine those two. So I combine those two together in series to get that. I combine those two together in parallel. Hey, look, now those are in series, and I can combine those two. I'll put S2. So that's the approach. Sometimes it takes a while because you've got to combine all these different things. Now let's look at this one. Oh my goodness, this is a lot going on, so this is going to take a little while. I'm going to list them all here. They all have different values, so that's okay. I'm just going to call this the 5, 2, 1, 3, 8, 4. I think I got them all. Yep. And the voltage is not 24 volts across each of them, right? 24 volts is between here and here. It's not between here and here, or here and here, or here and here. Now, some of these things are going to add up to 24, but we really can't use that 24 yet. So what we have to do is simplify. One thing that's really nice is those three are in series. This one connects end to end with this one, connects end to end with this one. Nothing's coming off the side. So I can now simplify this somewhat as 24, 5, 1 8, those haven't changed. And then here are these connections there, and I'm going to replace this one with this. And I'll call this C series 1, because we're going to have another C series eventually. Okay, and I'm just going to look up. I'm not going to sit here punching stuff into the calculator. I did the work earlier. And so when we simplify that, what happens is we end up with 0.923. So 0.923. And again, I don't know anything about the charges or voltages yet. Now I look at this, and that's a parallel combination. So I redraw my circuit. Yeah, it takes a while, but you want to make sure you get it right. Okay, this is still 24 volts. And then this is going to be my C parallel. Is just going to be 1 plus 923, sorry. There we go. So this is 1.923, and I'll call that my C parallel. All right, that is C parallel, C series 1. Then these are all in series, so I can combine those. So I end up with 24 volts, and this is nice, so we do 1 over 5 plus 1 over 1.923 plus 1 over 8 ends up being 1.18 microfarads. And that's my C equivalent, or I could call it C series 2. I'm just going to call it C equivalent. C equivalent. So now I've gotten this thing completely simplified. And you can see now that the 24 volts is across the 1.18 microfarad, capacitor, that equivalent capacitor. Now we got to kind of work backwards. Okay, so we've got 24 volts and we've got C. C equals Q over delta V. So I multiply these two together and I'm going to get 28.32 microcoulombs. Q equals 28.32. Well, remember, this came, let me write this as CS2. CS2. These came from series capacitors. Series capacitors don't have the same voltage, they have the same charge. Okay, so I can just do this, let me go back. So I want to make sure I'm getting it to the right ones. So the 5, 28.32, has a charge of 28.32. The 1.923 has a charge of 28.32. And the 8 has a 28.32. In other words, each of these, which I look up in here, have the same charge as each other. Now I can do this. I can use this to find the voltage, and I think that ends up being Q divided by C is 5.66. 28 divided by 8 ends up being 3.54. 28 divided by 1.93 is 14.75. Now notice something. The delta V across this, the delta V across this, and the delta V across this have to add up to 24. So if I went up 24 volts in energy going from there to there, I'd have to go up 24 volts going from there to there to there to there. 5 plus 3 plus 14, that's 21, 22. So it ends up being about 24. Okay, I've done some irresponsible rounding. So that's kind of nice to know. But we're not done. Now we want to get this, the C parallel. Remember, this replaced those two. Parallel have the same delta V as the combination and as each other. So whatever this one was, 14.75, I can apply to 0.923 resistor and the 1 resistor. They have the same delta V. Then what I do is, anytime I've got two, I do C and V, and this one's going to have a charge of 14.75. This one's going to have a charge of 13.57. And I just keep working backwards. So the very last thing I've got to do is now I've got to take this one, the series one. Remember, this will have the same charge as each of these. So the charges are the same. Let me put that, Q's are equal. This one, the voltages, delta V's, were equal. This one, again, came from series, so the charges were equal. Okay, so now the charges are equal. So the 0.923 charge, 13.57, is the same as on the 2, 3, and 4. And that's actually our last ones we have to do. 13.57, I don't know why I wrote 5.2, 13.57. Okay, so each of those, they all have the same charge. Then we multiply, or excuse me, divide it out, and we end up with 6.75. And we end up with, for the 3, it's 4.52. And for the 4, it's 3.39. Now, let me show you something about those voltages. It turns out anywhere you go around a loop, the total voltage has to be 0. In other words, if I go from here to here, it's 24 volts, right? Well, that energy change has to be the same over any of these branches here. So if I already did it with the delta V going around this one, let's go around that outside. If going from here to here is 24, positive 24, then these other ones should all add up to 24. The 5, the 2, the 3, the 4, the 8. So everything except the 1. So 5, 2, 3, 4, 8. And if we add those together, that's 11, 12.4, about 22, 23. So it does add up to about 24. Those voltages all add up the same. Okay, so that's a lot. This is a long one. This is a long one. In fact, I'm going to check my time here. Oh, it's so long. Okay, now let's come down here. Simplify drawing each step. Oh my gosh, I'm not going to do all the numbers. I will fill out the table, but I will show you that the first thing is to simplify these two in series, but you can also simplify those two in series. So you end up with this, right? Because those two simplify to that, and those two on the end simplified to that. Now I can't combine them all together all at once because they're not all 4 in series. Just this is in series with this is in series with this, okay? And then I can use those in parallel. Boom, 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 boom. Like that. And then these two will be in series. I combine them like that. And I will fill out the the capacitances that you should find when you get that. I've got them written down: 2, 5, 4, 3, 6, 1, 1.7, 2.7, 4.4, and 0.58, 50. Okay, and I'm not going to write down all the voltages, but I'll write the charges just so you see. 20. Actually, I'm just going to paste in the answer.